In this video, I want to talk about memory in AI systems. Modern AI models, including large language models, would not be possible without some sort of memory. They answer questions, recognize patterns, and generate new content because information from previous learning is somehow stored and later retrieved. This raises an interesting question. What does it actually mean for an AI system to remember something? The most common type of memory is memory stored inside neural networks. During training, a neural network repeatedly sees examples and gradually changes its weights. After enough training, information from the dataset becomes encoded in these weights. We usually call this process learning or generalization. However, neural networks are also capable of overfitting. Instead of learning general patterns, they can memorize specific examples. To demonstrate this, I built a maze-solving experiment. I intentionally removed all meaningful inputs and provided the network with only a state identifier. The network did not know the maze layout, coordinates, or geometry. It only received a number representing its current state. Despite this limitation, the network learned the correct action for every state and successfully solved the maze. In other words, the network became a compressed state-to-action memory. This experiment demonstrates that neural networks can function not only as generalizers, but also as memory systems. Another form of memory is a retrieval-based memory. Instead of storing information inside weights, we store it externally and retrieve it when needed. A popular example is retrieval augmented generation, or RAG. In RAG systems, text is converted into embeddings and stored in a vector database. When a user asks a question, the system searches for similar embeddings using cosine similarity and retrieves the most relevant information. Unlike neural network weights, the memory can be modified without retraining the model. My own experiments focus on associative memory. Instead of storing compressed information in weights or embeddings, I store individual memories directly. When new information arrives, it's compared against existing memories using similarity functions such as Gaussian similarity. If matching memory is found, it becomes activated. I tested this approach on simple color memorization tasks and on handwritten digits recognition using the MNIST dataset. In the MNIST dataset experiment, the system achieved approximately 72% accuracy, significantly above the 10% expected from random guessing. Although this approach is still experimental, it behaves differently from traditional neural networks and resembles a form of explicit memory retrieval. These experiments suggest that AI memory is not a single mechanism. Information can be stored in neural network weights, external databases, or associative memory structures. Understanding the strengths and weaknesses of these approaches may help us build future AI systems that learn, remember, and adapt more effectively.